So today we have the pleasure to have Fatos Xhafa from the UPC, the engineering school here in Barcelona. Special thanks Fatos because he filled in the gap that Celso gives, and he was very willing to come here and give a talk. So I really appreciate this effort to come here. So the talk is Meta-heuristics for calculus optimization. So you see a lot of applications in many different areas. So I leave the floor to Fatos. Thank you so much, Fatos.
All right, so good morning, everyone. You hear okay? Is okay? So, yeah, I'm glad to be here. As Elena said, I'm a little bit a speaker by accident. Actually, my plan was to come anyway, but I hope to see Celso, but anyway, so this time it could not be. So, this talk is about some meta-heuristics for cloud optimization. So as you know, this cloud computing thing has become one of the mainstreams in all the fields, not just the computing, but everywhere. Businesses, administrations, enterprises, science, engineering. So here we are again. We have to optimize with the cloud platforms. Obviously, some people may think that we are kind of inventing the wheel again, because we had, traditional distributed systems, supercomputing, and then we have cluster computing, and then we have grid computing. And in all these settings, we had to deal with optimization, especially with scheduling. So, it looks like each new distributed computing paradigm requires, again, to revisit and to look at the meta-heuristics. And the main reason for that is that each new distributed computing paradigm at large scale brings new features that were not present in prior or former versions of the distributed computing. For example, grid computing and cloud computing do share some things, obviously, but they are completely different philosophies, and they have different requirements. Therefore, we have to look at the meta-heuristics and see what the usefulness they can bring for cloud optimization. So I'll have structured my presentation in two parts, basically. In the first part, I'll talk about the use of meta-heuristics for the cloud optimization. I'll very briefly introduce some of the concepts of cloud computing to, I'm sure most of you are kind of familiar more or less with the cloud computing, but just to put the ground, I'd like to remind you some basic concepts. And then, so the main focus here is how this cloud computing needs optimization at the very large scale, but also from a multi-objective perspective, right? One new feature of the cloud computing systems is that we see a variety of actors, from final users to the stakeholders. Therefore, we have different optimization views, and we have to address sometimes these views either in a trade-off way, meaning having some compromise to satisfy all of them, or we have to target single optimization views to get the best of the optimization for that class of users. And to exemplify this presentation, I'll focus in one of the optimization problems that arises in cloud computing, which is the energy optimization, which actually is one of the most challenging optimization problems. Could be said that also that this is one of the new optimization problems, so differently from scheduling problems that have been investigated by optimization community for decades. Energy optimization in a computational infrastructure like cloud computing is kind of a new optimization problem. And through this, I'll try to exemplify the challenges and of the multi-objective optimization for the case, for the case of the energy optimization. Then in the second part, I'll show how meta-heuristics somehow meet the big data in the context of the optimization, right? So obviously, meta-heuristics are primarily addressed for the optimization in cloud computing, especially for scheduling, resource management, etc. But cloud computing and big data are linked together. Therefore, whenever we deal with the meta-heuristics, we may need also having meta-heuristics for the big data optimization. I'll introduce for you a kind of a new model in the cloud computing, which is data as a service. As you know, in the cloud, we can have everything as a service, and one of these services is data as a service, which can bring some advantages when we have to deal with the big data optimization. In particular, I'll introduce for you the data-aware scheduling, which becomes really critical in the context of the big data, essentially because we can't ship the data from one place to another one because they are terabytes of data. So differently from other distributed computing paradigms like grid computing, now you don't ship the computational task, the data and the program, right? And then at the end, I'll have a brief outlook on altogether meta-heuristics, cloud and big data and the optimization. Obviously, I'm not going to enter into technical details. I'll give you some technical details, but mainly I'll try to give you some highlights. So I guess most of you are PhD students or are young researchers. So hopefully after this talk, if you are investigating in this field, you can have perhaps some new ideas. And if you are not investigating, perhaps you can decide to catch up on this new and very exciting field, right? All right, so first of all, let's see a few concepts, very basic concepts for cloud computing. So the main feature of the cloud computing, differently from traditional large-scale distributed computing systems, is that cloud computing platforms have the ability to deliver computing services on demand. And when I say computing resources, there is everything. So it's from a high-level application to data centers, computing resources, networking, data storage, etc., right? Another feature or distinguished feature of cloud computing is that software in cloud computing is structured in a stack where we find different layers, right? So we have the lowest layer, which is the infrastructure as a service. Then we have mid layers like platform as a service. On top of that, software as a service. And then on top of that, we can put everything as a service. So you can have application as a service, meta-heuristics as a service, knowledge as a service, analytics as a service. So you put the name, right? So, and this is thanks to this stack organization of one of them actually is the data as a service, which I'll introduce later, right? So the fact that this organization into layers makes possible that we can deliver on-demand computing at different levels and according to different needs. For example, there might be some users, an enterprise, that basically want to run existing software in the cloud. Therefore, they can go to the software as a service. Some others, in an enterprise, for example, would like to have a full cloud environment to be able to develop and deploy the full cycle of its software, right? So web services, web servers, etc. So they would go to the platform as a service, and then there are others that may need networking services, data storage at a lower level. There they can go to the infrastructure as a service, right? And all this is done thanks to the capability of the cloud to manage the resources in an elastic way. It means that you can scale up and down according to the needs of the users. Obviously, what is propelling this cloud model is the business. If those who might remember grid computing systems or have read some papers for grid computing systems, you'll remember that grid computing was basically for scientific communities, doing experiments, doing data processing at large scale, but grid computing was not able to penetrate into the business model. Obviously, that was not easy. But the idea of the grid computing with the virtualization of the resources was caught up by the community and was developed through the cloud computing. So, and obviously, there is a pay-per-use model. You pay as according to the use. And in most cases, we have a kind of a support of a self-service, means that you don't need to have human interaction in order to set up your cloud platform, right? And finally, the quality of the service, which is one of the most interesting and important parameters in all distributed computing systems, now is a kind of more formalized, because it's a kind of a contract between the cloud provider and the user, right? And this is usually known as the service level agreement. So service level agreement is a kind of a contract when they guarantee you somehow what the bandwidth that you'll have, what the storage capacity that you'll have, what is response time that you'll have, what is the security level that you'll have, et cetera, et cetera. So the complexity of the service level agreement depends obviously on the demanding requirements of the final user, the type of application, et cetera, right? There are different kinds of cloud computing models. This is important to have into account, because when we'll talk, for example, about the service level agreement, this formalization, this contract could be one thing for a private cloud, could be another thing for a public cloud, and could be a completely different thing for a federated cloud, right? And obviously, this has a direct impact also on the optimization problems that we might wish to solve, right? So basically, the public cloud is owned and operated by companies that offer rapid access over a public network. You can think here, I mean, all sorts of Google and Amazon, etc., that offer services through their public cloud. We have a private cloud, for example, Technical University of Catalonia, or I guess Universitat Pompeu Fabra has its own private cloud, mainly for their users. We can a hybrid cloud. Most of the, I mean, if you have a private cloud, you'll have to connect to some public cloud, because you have to share and combine the services, not only from the private cloud. You'll need also the public cloud, right? And a new trend is the federated cloud, right? So everything is getting larger and larger. So, which means that we have multiple cloud service providers, and they somehow federate together. If we'll have to, this is actually an interesting model from the optimization perspective, because assume that the objective is to optimize the provider's benefit. All right. Now you have an array of providers here. So you have to optimize the benefits for all of them. So, and you can quite easily think here of establishing a game among the different providers, which are obviously can play their own strategies to optimize the profit within the federation, right? And you can also have multi-cloud, which is different from federated clouds. We have several clouds here, but they are not, here are under a federation rule somehow. And here there are no any combination, so they are not binded to any federation rule, right? Another concept here is the data center. Let me just briefly bring it to your attention. Basically, to stress the difference between what's the main difference between the data center and the cloud computing, right? So the main difference is that in a data center, everything happens on premises. So we do have the hardware and software solution, but all of them are within bounded premises, let's say, of certain enterprise, right? In difference, the cloud computing in general runs on off-premises, so it's completely virtualized. You don't know where the physical resources are. You don't know where that storage capacity that you are granted is, in which machine it is. You don't know where the software services that you are given, in what machine they are, right? And actually, not only you don't know where they are, they can migrate from time to time, right? So you cannot track, if you know somehow, you cannot track where your services and your data is stored, right? So this makes a little bit of a difference because for the case of the energy optimization, it makes more sense to address this for data centers rather than for the cloud computing in general, right? So is it because actually in a data center is a kind of an in-house administration, and then you have a sort of kind of administration that is interested in reducing the energy consumption for the premises where the data center is running, right? All right, so well, the big question, or as Spaniards say, la cuestión de un millón, or la pregunta de un millón, is what can be optimized, right? Well, you can, as you see, so this is a whole array of things that can be optimized. And this array of things that can be optimized goes from traditional distributed performance objectives, which people that have worked for decades on distributed computing are kind of familiar with. Like you minimize the make span, which is the latest finishing time of tasks. So assume that you have n tasks and you get the latest finishing time of the latest task, well, the finishing time of the latest task. So, and you want to minimize that, right? That would give you the make span. You'd like to minimize the flow time, which is the sum of the finishing times of all the jobs. So it gives you a sort of indication of the system throughput, also of the quality of the service of the whole system. You may wish to maximize the resource usage. Every distributed system very easily becomes heterogeneous. So you build up your own cluster, right, your private cloud, and then after 5 years you keep upgrading, right? You can upgrade vertically, you can upgrade horizontally. Vertically means that you add more resources to your servers, or you add more machines, more racks, etc., right? So very easily in a 5 to 10 years time span, it depends on, of course, every organization, you get very easily to a heterogeneous distributed infrastructure. And obviously, you'd like to maximize the resource usage because you cannot, so we run here into conflicting objectives. As an administrator, you'd like to give usage to all the machines, but the user would like to use the fastest machine because that would provide him with the fastest response time, right? And then you can think of other scheduling objectives. For example, you can have resource provisioning in advance, or you can make resource reservation, especially for a kind of tasks which are known as periodical tasks. For example, you may have one big company like Repsol in Spain, where they know that they have to process every month one very large file. Obviously, in this case, you can make a provisioning of the resources, of course. But because it is a very large scale, and you may have many users that have periodic tasks, then we'll have to have an optimization on that context too. The other array of optimization objectives is the one from the provider or the stakeholder perspective. So the cloud providers are obviously interested to maximize their profit. This is what they are doing the business at the end, right? And of course, if you have a multi-cloud or if you have a federated cloud, you'll have a multi-providers. So you'd like to, as I said before, to optimize the profit of an array of providers. In this list, we could put also the minimization of the energy consumption. This is directly linked to the profit. So if you reduce the energy consumption, obviously you reduce the cost so you increase the benefit. This has also another indirect benefit for the IT infrastructure. So the fact is that, and it is a proven fact, that the heat due to high temperatures, I mean due to the high computing activity in the data center, with the time bring to a degradation of the IT infrastructure. So obviously, this is why energy is really critical, not only for reducing the cost of the data center, it is also critical to extend the lifetime of the data center, right? And then another one could be, for example, to maximize the service matching. Service providers, or I mean cloud, can offer many services, many. So many times the users would like to have one service, and they have an array of possibilities. So which one to take? Let's say I want a Meta-heuristics as a service, and I say that there are an array of services on Meta-heuristics. Evolutionary computing, local search-based heuristics, or I don't know, game-based optimization, linear programming optimization, etc. Right? So in that case, cloud providers are interested also to maximize the service matching. Means that to have the best fit between the user's requests or requirements and the service that can bring that, can give that service, right? And finally, perhaps most important is the user-oriented objectives. As you know, no cloud can exist without clients. So client is one of the foremost objectives in the cloud system. And then we can have to minimize response time, to minimize the user's cost. Remember that this is a pay-per-use platform. You have to reduce maximum the cost of the user so that you can have the user in the loop all the time. And to maximize the service level agreement. So obviously, this is a little bit of a ambiguous and critical point, but because there are not mechanisms so far to fully ensure that the service level agreement is ensured. Like, for example, when you contract at home, let's say an internet service, they say you'll have a 30, I don't know, megabytes, and then there is no way that you can prove somehow that you have exactly always that amount of bandwidth, right? But at least, if not, you don't satisfy fully the service level agreement, you should try to minimize the violation. So sometimes there could be some fluctuations or some violation of the service level agreement, and then obviously you should try to minimize that. All right, so as you see now, so what can we say? There are so many objectives here. And this could be seen as one single big optimization problem. Ideally, we should optimize all these resources together. Now, what's the point? First, there are many issues here. So the first issue, which could be seen as new issues in optimization field. So the first issue is the large number of objectives to be optimized. The more objectives you have means that the more variables you have means that the larger is the solution space, right? So it becomes really highly constrained, but at the same time, the solution space, which is usually even for, basic NP-hard problems is exponential size. Here it becomes huge, right? Second thing is that most of these objectives are conflicting. So if you try to maximize the resource usage, that would be very good for the provider, right? Because he is giving usage through the whole infrastructure and is doing business and money with that. But that contradicts the response time, as I said before, right? For example, you could try to minimize the inner sequence and to minimize the energy, right? So one simple thing or one simple strategy to minimize energy is migrating, as I'll show next, migrating virtual machines from one server to another one. So that assume that, for example, you have two servers and you have 9 applications running in server A and 1 application running on server B. What would be the interest of the cloud provider in this case? To migrate the single application running on the server to the server which has 9 applications. This is very good to optimize the energy, but this could violate the service level agreement. Why? Because due to this migration, there is some time to make the migration, and the resources that might be found in the new server might be not necessarily the same quality as they were in the previous server, right? So the fact that you can easily run into conflicting interests by optimizing one or minimizing another objective makes the problem really challenging. So the question is it possible? Is it possible to address all these objectives altogether? Well, you can, but for practical purposes, it's really not reasonable, right? So in most papers that you will see in the literature, you will see where meta-heuristics are addressed partially to solve some or to optimize some of these objectives, right? In some cases, you can, I don't know, for example, if you optimize some objective, you may also optimize by indirectly also some other objective, but altogether, this is the objective, the optimization problem that we'd like to solve, right? And this is really a very complex one. Now, I don't know, I have to remember you that even scheduling n jobs into 2 machines is NP-hard problem, right? Scheduling n jobs into 2 machines is NP-hard problem. So now you can guess the complexity of the problem now. All right, so as we have a number of objectives, and objectives, so the question is how can we optimize? So even if we don't decide to optimize all the objectives, we have to optimize some of them, right? So what kind of optimization approach can we plan here? Well, basically there are 2 approaches. One which is not very much used but is useful, which is known as hierarchical optimization. And the other one that I'll show next is the simultaneous optimization. So in the hierarchical optimization, because we have a number of objectives, we establish some priority among the objectives. So I say F1 is the most important one to me. F2 is the second most important. F3 is the third most important, and so on, until the Fn is the least important objective for me. For example, if I were a cloud provider, I would say F1 is my top priority. I want to maximize my profit, okay? Saving energy would be my second priority, or minimizing the service level violation would be my third priority, right? So according to my view, I establish a priority on the objectives that I would like to optimize. What is this useful for? Well, then I can establish a hierarchical mode optimization. First, I optimize a single objective optimization, F1. And I can do any kind of, well, all the array of meta-heuristics from population-based to local search and others, right? Once I optimize F1, I try to optimize F2 without worsening F1. So the condition is that, assume, for example, that you have optimized F1 and now you are optimizing F2. Now you could put a condition like this as follows. When exploring the neighborhood, whenever you check a new solution, you accept that solution if it doesn't worse the F1, right? And so you optimize the F2 and then you stop somewhere. Then you optimize F3 with the condition that you don't worse F1 and F2 and so on until you cover all the objectives, right? So what is the advantage of this approach? First, you are dealing every time with a single objective optimization, which is much faster and much easier to handle, right? And then you have a number of, it is easy to implement because you basically have a loop. actually it's sort of efficient because whenever you, by moving from F1 to F2, you are kind of reducing the neighborhood because you are restricting only on solutions that do not worse F1. When you move to F3, you are restricting a little bit more because you are reducing to all solutions that do not worse the F1, F2, and so on, right? So you're easy to implement, it's useful, it's efficient, and it's very suitable if you have one single optimization view, like final user view, stakeholder view, provider view, or performance view, let's say. Right? But in this case, obviously, you have to have this kind of priority among the objectives. So you have to say, well, this objective is my top priority, and then you should be able. So if you are not able to establish this priority, obviously, you need to move to the more used one, which is the simultaneous optimization, where you optimize all the objectives at the same time. Now, how can you optimize, let's say, 10 objectives, or even 3, or even 4, right? Well, you can have two modes. The first one would be that try to reduce 10 objectives into one single objective. So the advantage of one single objective optimization function is that actually it's much easier to handle, and it is also much easier to interpret, because remember that if you have a Pareto front, you don't have one solution. You may have an infinite number of solutions. So at the end, you may need someone, like some kind of an expert, to say that from the Pareto front, get this one and this one and this one, right? So in that case, so the first approach would be, if possible, is to sum up the n objectives by multiplying them by some factors, right? Lambda 1, F1, lambda 2, F2, lambda n, Fn, right? Obviously, you have to have the condition that all lambdas should sum 1, and they are positive numbers. What's the problem or the disadvantage with this approach is, first, that you are introducing a new restriction, which is the one for lambdas, and you are introducing n additional variables, right? The other problem is that, and then actually this is the most difficult point to solve here, is that, is it possible to sum up n functions? It's not always possible. You have to sum money with time, or you have to sum CPU with watts, right? So you have to sum seconds with something else, right? So the different objectives are not measured with the same unit. So you need to find a way to transform and to normalize units of different objectives so that you can sum them up. For example, I could transform, assume that I would like to optimize the energy consumption and the resource usage, right? Then energy consumption is measured in watts, terawatts, for example, per hour, and CPU usage, I have to transform it, I have to have a function that shows me for 1 hour or CPU usage what is the energy consumed, right? And then I can sum up both of things. The other difficulty here arises how to find these lambdas. That actually introduces a big question. Obviously, you may have some kind of prior tuning, prior experimental, using traces from the distributed system, or use just human experience, right? So the thing is that the values that you'd use for lambda, and these obviously are an infinite number of combinations. I mean, if you accept these just positive values, makes difficult to find what is the best one. But anyway, it's always a kind of compromise, right? So if you reduce from 5 objectives to just one objective, which simplifies you the life. But obviously, you have the additional difficulty that you have to find what are the best values for lambdas, right? And if you cannot do this, then you go to just, this is the the Pareto front solution where you can always handle a number of objectives at the same time. And then you compute the Pareto front, right? But as I said before, finding the Pareto front solution is not easy. Obviously, there are off-the-shelf meta-heuristic solutions from genetics and to other families of meta-heuristics. But at the end, you'll have to find some kind of a trade-offs for different objectives, right? So it might not be possible, especially in the case of the cloud computing. This is an important observation. So when you solve the problem, you don't want to have human intervention, because if you remember at the very beginning, I said that this should be a kind of a self-service success, right? So it's impossible to think that Amazon will have someone else getting the phone for you, right? So and then if you want to have a self-service success, means that all these things have to be run automatically, and decision makers and the decision has to be done, on the fly, not by a human decision maker, right? Okay, so far we have seen a few basic concepts for the cloud computing. We have seen a general formulation of an optimization problem on clouds, where we have a number of objectives to optimize. And because we have a number of objectives to optimize, we may have either an hierarchic optimization mode, or where we optimize according to a priority established a priori, or we can adopt a simultaneous optimization, either by reducing to a single objective or by using a Pareto front solution. Okay. Now, to exemplify a little bit more the complexity of the optimization problem in the clouds, I'll give you some highlights about optimizing the energy in cloud data centers. Right. Sorry a moment. All right. So from the previous exposition, you notice that energy consumption is actually one of the key objectives to optimize in a cloud computing. Nowadays, this is actually becoming a real headache for large cloud computing systems. So the point is not to make your cloud platform bigger and bigger. So that's easy somehow. The problem is who pays the bill, right? Obviously, the cloud provider has to pay the bill, but the cloud provider may charge that bill to the services, right, to the final user. So the problem is that you have to have this cloud energy optimization, because according to the some projections, let's say for 10 or 20 years, the energy consumption in cloud data centers actually is going sort of, well, not exponentially, but is exploding to in a very, very fast mode, right? So as you see, for example, the global footprint for the electricity usage by 2020, compared to, let's say, 10 years before, 20 years before, is huge. And the amount of the data centers and servers that are being deployed worldwide keeps increasing every day, right? Obviously, this has a huge impact not only on the cost of the providers. It doesn't have also impact only on the IT infrastructure per se, due to the heating, but it has obviously a huge cost for the environment. And so there is a whole trend of energy-aware computing or sustainable computing, which aims actually to reduce the energy on data centers. One of the ways to, at least from the optimization perspective, to reduce the energy in a data center is to use two key features of the data cloud, so the cloud data center. So the first is virtualization. And the most importantly, this new feature, which is the virtual machine migration. So the virtual machine migration means that your application is running into a virtual machine in a server, and at some point you can decide to migrate, to make a live migration of that virtual machine to another server, right? So this is one of the most used techniques at present, so that you can make load balancing, and you can implement policies of switch on and switch off of the servers. Obviously, by switching off a server, you can have a drastic reduction on the energy consumption of your data center, right? So just to simplify a bit, we could consider this three-layer data center architecture. On the top layer, we have the application, which could be called application layer. Means that applications comes in independently from different users, and the application placement layer is in charge to place one application to one of the virtual machines, right? So obviously, you can have various policies of placement. Say you can have first application, first server, second application, first server, third application, first server. This server is full, then I move to the next one. But this policy obviously doesn't work, because you have a service level agreement, and then you have every application has its own requirements. For example, this third application might not be possible to run here. Why? Because of data storage, bandwidth, computing capacity, etc., right? So you have to find a sort of a matching between the applications and the virtual machines that you have in the data center. And then we have this is actually just to compute where every application has to go. This is a kind of a combinatorial optimization problem. But then you have another optimization problem. So once you know that this application has to go to this virtual machine, the question is where has to be placed this virtual machine type, right? So the idea is that cloud providers manage an array of virtual machine types, and then you make the matching, the best matching between the application and virtual machine types. And the point is, once you find the matching, where do you place the virtual machine, right? So we could see this as a kind of a double optimization problem, or a two-phase optimization problem. So the first one is you have to optimize the matching, or the placement of the applications into virtual machines according to different types of virtual machines. And the second one is you have to place the virtual machines into physical servers, right, according to the characteristics of every physical machine and according to the characteristics of every virtual machine, right? Now, if we'd like, if we'd like to formalize this a little bit, because as you know, if we'd like to run an optimization meta-heuristics or linear programming or whatsoever, we have to formalize and say what is the instance of the problem, right? So we can formalize the instance of the problem in the following way. Assume that we have a number of servers, right? So, for example, we have a number of 10 servers in the cloud center. And every server can run a number of virtual machines, right? So we know these numbers here, and we know these numbers here. Then we characterize every virtual machine by a number of parameters or analytics, or somehow we make the profiling of the virtual machines. So the profiling says that what is the CPU of the virtual machine, what is the memory, what is network bandwidth, what is the million of instructions per second of that virtual machine. That could be very useful then to express performance parameters. And then if you wish, you can have also other characteristics, like what is the reliability of that virtual machine, what is the security factor of that machine, etc., etc. Right? So once you have these analytics for virtual machines, so these are numbers. Actually, I'll show you next, you can get real numbers for virtual machine characterization. Then we have a number of tasks of applications which are submitted by users independently, right? How can you characterize a task or an application? In the same way that we can characterize virtual machines by MIPS, which is millions of instructions per second, we can characterize an applications by MIP, without the S, which is millions of, well, actually MI, which is a million of instructions. So somehow you express the whole computation that you need to complete the execution of that application, right? So let's say if you want to multiply two big matrices, you can actually compute or estimate what is the number of million of instructions that are needed to complete the multiplication of two matrices, right? Then we have this feature that the virtual machines can be migrated from one server to another one, and we have a service level agreement, right, as a sort of a requirement. For example, we can have, let's say, response time bounded by some number. For example, at least the response time has to be this. We can have other requirements like the bandwidth has to be at least this, or the storage has to be at least this, etc. Right? So, and then under this instance of the problem, the objective here is single objective, is to assign the incoming tasks and applications to virtual machines by using the virtual machine migration, so as to minimize the energy consumption of the data center. Obviously, we are not ignoring these service level requirements here, right? The objective is actually to minimize energy. So, and I'll show you several meta-heuristics that can be used for that. But the objective is to see also if some meta-heuristics perform fine for minimizing the energy, how about the service level agreement? Do they violate a lot of a little or a little the service level requirements, right? Okay, so we have one problem formulation, and now we need to find a model to solve or an optimization approach to solve this. One first approach, for example, could be to model the energy consumption as a bin packing optimization. The reason to consider this bin packing optimization or formulation is that I don't know if you are a little bit familiar with the bin packing, which is one of the most classical problems in optimization theory, is that there is a huge amount of research done for the bin packing. So since 60s, bin packing has been one of the most studied problems, right? So how can you formulate this problem as a bin packing? Remember that we have two optimization problems. One is for placing the applications, matching the applications with the virtual machines, and the other one is placing the virtual machines into the physical machines, right? So for the first one, for the application assignment, you can consider, for example, that the weight of every so we have, remember the bin packing, so we have a number of items, let's say n items, okay? And we want to put, every item has a weight, and we want to put these items into bins. Obviously, we are interested to minimize the number of bins, right? And obviously, we have the restriction on the capacity of the bins, etc. So for the application assignment, we can consider that the weight of an application is the number of million of instructions per second. If you, we could use also just the amount of the memory or the CPU, or we can make a combination of them, right? Like just summing them up, for example. An item is an application, and the bin is the virtual machine. So this is the virtual machine, right? And then we try to put different applications in this, into this bin. For the second optimization, we could use the weight could be again million of instructions per second. Now we can add also storage and bandwidth, because remember that in the second we are closer to the infrastructure level or network level. And we can try to make this, so we have two bin packing problems here. And we can try to solve this problem. We'll, of course, we'll get a sort of optimization for the problem. Now, the issue here is that this is a little bit of a simplified model. So it's not easy to take into account, let's say, all these servicing level agreement, etc. Right? So, but it could be a first approach. So, for example, if you'd like to, use some first model for the energy optimization in a cloud data center, you can just start from here, right? And you get some solution, and you can evaluate if that solution is good for the purpose of the data center, right? Now, from the meta-heuristics, which is actually the topic here, we could do the following. So first thing, we have to decide whether we are going to do things in a static setting or we are going to do things in a dynamic setting. So in the static setting means that we take a snapshot of the data center and we use the information of that snapshot for the whole, for building the problem instance and for solving the problem, right? In the dynamic case, obviously we cannot use a snapshot because in the meantime that we are doing computations, that snapshot has changed. So the load of the machines, for example, has changed due to migration, all these things. So there is a dynamic setting where things keep changing, and the snapshot doesn't give you the correct view of the system, right? So anyway, remember that we have a two-phase optimization problem. So in a static setting means that we already know what are the applications already in the system that has entered into the system. And the first thing is to make the assignment of the task or the applications to various virtual machine types to optimize here the energy. And then once we have we know this assignment of applications to virtual machines, we have to make the second optimization, which is placing the virtual machines into the physical servers, right? In the dynamic case, we'll have to have into account more information. For example, we need to know what is the load of the host. And this information is important because according to the load that we may have at different servers, we may activate the migration. The idea is to switch off some of the servers in the data center, right? But again, we have the optimization of the two problems, right? The only difference is that everything here is static. So we make the picture, we take the snapshot, we have the numbers, we run the problem, we get a solution, right? In the second case, we have to get the information dynamically, right? And cycle continuously because this is a loop, right? So we get the current information, we optimize, we check again the system parameters, and then we cycle, right? So obviously, during this cycling, where we are getting that optimization or the energy optimization. Now, two other details in this picture. Assume that you have implemented all these things, right? So you have some nice meta-heuristics here, some other nice meta-heuristics here, and here, and here, and here. So you can optimize through meta-heuristics all these blocks, okay? The second critical point is where to test or where to evaluate these things, okay? So obviously you can do that in a real cloud, but that's really complicated. So no one in a real cloud is going to allow you to make switch on and off servers because you are doing, kind of optimization, right? So the best thing here is to get some simulators. There are several simulators for cloud computing out there. One of them is actually the Cloud Sim, and if you'd be interested on investigating on this field, I would recommend you to start with Cloud Sim because you'll find there are most of the features. Obviously, you have other choices for the cloud simulators. And then for the static case, the problem is that you need to build the instance, right? So you need to get the numbers here. So in order to get these numbers for the number of machines, parameters of the machines, etc. Obviously, you'll have two possibilities. So one would be you just generate number randomly. So generate CPU according to some distribution. You generate bandwidth according to some other distribution, etc., right? This would be fine to test the meta-heuristic, but remember that random instances usually, most meta-heuristics perform usually very well on random instances. It's very difficult to capture the characteristics of the problem by random instance generation. So in that case, it's much better if you consider some traces from like cloud computing platforms. For example, Planet Lab is one planetary large-scale distributed system, and there are public archives where you can get the traces of the Planet Lab. There are workloads from parallel computing community, so you can find real life traces, and then you can get those real numbers that give the profiling of the CPU, the bandwidth, etc., etc. Right? Obviously, you are kind of approaching with much better, the testing of the meta-heuristics rather than using the random number generation, right? And then obviously for the dynamic case especially, you'll need the simulator, because you need to make changes in the system, and then you need to loop, right? Okay, so very briefly, because I think I'm getting a little bit more time than I thought to talk on this part. So as I said, in every block you can put meta-heuristics, right? Now, if this part, basically you have a number of applications and you have a number of virtual machine types. So this is some kind of optimization problem. So this is not affecting directly the infrastructure, right? So this is a kind of for making the best matching of the applications and the virtual machines type, right? So in that case, it is most suitable to use some kind of a heavy meta-heuristic. With heavy, I mean some heuristics like genetic algorithm, population-based meta-heuristics that would take some time to converge to optimal solutions, but that would bring some high-quality solutions for this placement, right? For example, just as an example, we have implemented some genetic algorithms here for this matching. And as soon as you start implementing the algorithm, you come to the point of implementing the genetic operators, right? You have to implement a crossover and mutation, and you very soon realize that by making, let's say, a single mutation, just a swap between two applications and virtual machines, that solution is not feasible, may become not feasible, because you change the virtual machine type, and perhaps that application or that virtual machine type is not suitable for that application, right? So, and you run easily into infeasible solutions. Then you have two choices. Either you decide to move only into feasible solutions, so you discard that solution. Or you say, okay, I would accept that, I would admit that solution for the moment, and I'll repair it. So repairing is basically saying that, okay, when I make a move, that application, that solution becomes infeasible. But then what I can do is keep moving until I find a server or an application, sorry, a virtual machine where that application fits into, right? And actually, this is what we used in the implementation, because this gives the applications, the genetic algorithms, interestingly, two good features. First, efficiency. It's not, time-consuming, very much time-consuming to repair the solution. And second one, so as a by-side effect, we are actually perturbing the solution. And this perturbation produced a high variety in terms of the genetic information in the solutions. So that contributed to keep a high diversity in the population. And that, as you know, if you keep a high diversity in the population, you are kind of controlling the premature convergence, which is very important in the case of the population-based algorithms, right? All right, so there are other technical details that I'm skipping here. So, and then in the same mode, we implemented for virtual machine placement. There are several people interested, actually. These are very recent algorithms proposed. And similarly, we passed to the dynamic version. So I'm skipping this because I think we should finish at 11, right? Yeah, so, and then we used, these, for the experimental design, a few key observations. First, as I said, we use the cloud sim because in the cloud sim, actually, you can simulate a data center. You can have deployed different. You can actually consider different deployment models. If you remember, I said we have public, private, hybrid, federated, etc. So if you wish, you can consider this also. You can extend the simulator via. It's a Java implementation, so you can via inheritance. You can implement or extend the classes. And obviously, one of the most important features is that you are kind of alleviated. You don't have the burden of the low-level details. So you just run into a more abstract model, right? And obviously, another interesting thing is that in the cloud sim, for example, you can have the quality of the service model, right? So you can measure what is the performance degradation due to the virtual migrations, for example, right? And you have service level agreements, some variations of the service level agreements, etc. So altogether, the cloud sim would give you a nice environment for testing the meta-heuristic, right? All right. Obviously, when you make the experimental design, you have to try to consider as many scenarios as possible that would capture the realistics of the data center. For example, you may start with an empty data center, and then you end up having a full data center, right? So obviously, the optimization at the edges is different, right? When the data center is empty, you may have a high optimization, easy to optimize. When it is full, it becomes very difficult to optimize, right? So very briefly, the second part, these meta-heuristics and the big data. As you know, big data means, what big data means for me not necessarily means for you, in the sense that my cloud data center has certain capacity, and of course at Google or at Amazon, they have another view for the data center because their capacities are much larger, right? So the key point in the data, big data, is not only the size that, of the data that you do have in the disk now. The point is if you are able to accommodate the generation rate. So if I have, let's say, 1 terabyte today, and I'm fine because I have a lot of disk, how about from now to, let's say, 5 years or 10 years? It depends on the data generation rate. If you expand the number of clients, if you have online transactions, that amount of the data could be very easily increased exponentially. So you have to have into account this data generation rate. And actually, this is one of the most difficult headaches, or this is one of the most challenges, biggest challenges in the IT, right? So the continuous data growth. So the problem is that sort of you are not able to, most of the companies are not able to project what is the data growth for their business. So perhaps Amazon, Google, even the big companies are not able to project that, but they can much easier make scaling of their data structure because, of course, they are giants of the cloud computing system, right? But for small and medium-sized enterprises, finding this data growth projection, it's really very complicated. And for your curiosity, there were some people that tried to formulate this Moore's law for data in the same fashion that Moore's law for data processors. So Moore in 70s said that the number of processors can be doubled. Well, the number of transistors to be packed into the CPU would be doubled every 18 months. And that kind of empirical law hold for many decades, right? This doesn't work for the data. So because, as I said, it's very difficult to make this projection for the data growth, right? All right, and then diversity of the data is another big challenge. So you have a variety of data types. So you have biological data, positional data, environmental data, video, voice, etc. Right? So altogether, this make the big data processing much more complicated, right? So now, what has this big data to do with the meta-heuristics? Well, you have to run an application, you have to schedule that application that processes the big data, right? Traditionally, in distributed computing, when you said task A goes to machine B, task means that in the task you pack the program and the data, right? So, and then you ship the whole thing. You pack at the master node the data and the program, right? And then you send it to the slave node, and then slave node unpacks the task and then runs that program on that data. Or you have to deploy the data beforehand into different nodes, etc., right? So now, is it possible to do that in the big data case? Impossible. If you have 10 terabytes of data and you want to process it, obviously you cannot pack hundreds of gigabytes into one task, because the transmission time would be higher than the processing time. And if the transmission time is higher than the processing time, what's the point of using a distant node? You run it in local, and that's it, right? So the parallel computing or distributed computing is useful whenever, by using more nodes, you can process faster. But if the transmission times surpasses the processing time, then you gain nothing, right? So here it is where this scheduling comes. So there is now a formulation of the scheduling which is called data-aware scheduling. Yes, so there is data-aware scheduling means that we need to process some data. We cannot send the data from one node to another one because it would take a long time. In some cases, even we cannot send the data because of protection policies of the data. You cannot move data from one facilities to another facilities. You can less move the data from one country to another one, so you cannot make cross-border of data movement, etc. So the idea is to make the scheduler to be data aware. Means that instead of moving the data to the computing node, now the trend is to do the vice versa. So to push the services to the data node, right? And this is actually what does the MapReduce somehow, right? Now, in the case of the MapReduce, if you have one cluster at UPF, that's easy because you are within one domain. Transmission time is fast, so you can do that. But if you move to a more federated context, which is the most general context of the cloud computing, that becomes a real challenge. So one of the ways to handle this is a new model which is called data as a service based model. So data as a service model, cloud model, started actually with enterprises. There are enterprises whose business is selling the data, right? And then you are, let's say, a marketing company, and you want data from customers, right? Obviously, they are not going to give you the whole data, because they may have data for customers from all over world, right? But you are interested only on the customers from Spain. So in that case, you can query data only for customers from Spain. So in that case, this is where data as a service entered into play. So they can serve you only a portion of the data which matches your query, right? After starting in a business context, this data as a service model now appears to be also interesting for implementing data-aware schedulers. And the model is more or less as follows. So we have a kind of authority that we could call data as a service layer, which is in the stack, that would sit in between platform as a service and software as a service, for example. So the first step is that you want some data, right? There is a query to find some data. And then once you find the data, right, in one of these cloud data centers, the point, and assume that the data is here. So instead of moving the data, the idea is to push the processing services to this cloud data center, right? That would be the easiest scenario. So here we are assuming that computing services can be run into this cloud data center. So the data is here, and we push the computing services here, and then we process the data. But it's not always possible, because assume that the data is here, and what you want to run is a workflow. But the workflow, it's not possible, so the computing service is not possible to run here. So in that case, at least what you can do is, again, you identify the data. You cannot push the service here, but what you can do is you can find the closest computing node, the closest in terms of data transmission. So it would take less time to ship the data from one node to another one, right? And then you can have a kind of a parallel transfer service that would send the data to the computing nodes. So, so two scenarios, briefly. One scenario is you identify the data that you want to process in the data center, and then you send the computing services to run on that data center. If that's possible, that's fine, because you can process the data in the data center. If that's not possible, then you have to ship the data to the closest computing nodes. And the closest computing nodes would be those that, in terms of the transmission times, are the most efficient ones, right? All right, so obviously you have now to consider some data functions like reading, transmission, etc., which should be part of the objective functions when you set up your scheduling problem, right? And finally, a brief outlook on this multidisciplinary field of meta-heuristics and cloud and big data optimization. This is really optimization is obviously, has always been a key point in all systems. You need to optimize. But as the systems, especially distributed systems, are becoming each time more complex and are serving each time a larger number of users, the optimization is becoming challenging. It is also becoming more challenging because the requirements are becoming each time more demanding. So we didn't have in the past service level agreements to run things in a cluster. We didn't have energy consumption, which is at a very critical levels in some data centers, right? So all these new requirements are making the optimization problem very much complex, right? In the Evolutionary Computation Congress in 2015, one of the competitions that was admitted was big data optimization competition, right? So if you'd be interested on this, you can have a look at this paper, and obviously for the case of the evolutionary big optimization, right? So that is means that there is a community behind. I mean, most of the community that we're using on meta-heuristics for distributed computing are moving to, but because even those that use to work, for example, optimization in logistics or other fields, because of this mixing with the big data, are, you know, all things are getting mixing together, right? So in some sense, so we could say that yes, cloud and big data optimization are meeting meta-heuristics. So meta-heuristics are one of the key techniques to improve the system's performance in the cloud computing from different perspectives of the cloud users, right? And finally, some recommendations. If you'd like to consider or investigate some problem in this context, some of the recommendations that I would briefly recommend to you are, when you formulate the problem, first look at the static versus dynamic case. So these are to make the optimization very much differently. So if you, usually most people start with a static case, so you do have the instance problem before the hand, and then you optimize, right? So that would be useful because you can get some clues on the complexity of the problem and what are the problem at the optimization process. Then, obviously, the most challenging one is the dynamic one. Here, you also need to not only simulate the dynamics of the system, but remember that dynamics could have also a variety. So you could have a very much changing system, or a system that changes periodically, et cetera, right? Then, if you, as we saw at the very beginning, the problem is multi-objective in its general formulation. So if you may wish to look at one single optimization problem or the multi-objective version, right? If you choose to deal with a multi-objective case, then you have two other choices. The hierarchical model, where you establish a priority among the objectives, or you try to optimize them all together, right? In some cases, this selection is done by, or is guided by economic and business value as well, right? So my top priority is money, so then the rest of the objectives are fine. If I can optimize them, it's fine. If not, no problem, right? One of the key points in such context is that whenever you implement a meta-heuristics, either population-based genetics, evolutionary, local search, variable neighborhood search, etc., you have to ensure diversity of the solution. Remember that premature convergence or getting stuck into local optima is what kills most of the implementations, in the sense that you have a premature convergence in 10 iterations of the genetic algorithm, and maybe you are running the algorithm for hours without getting nothing new, or in the case of the local search, you get stuck into some local optima, and then you are moving up and down in the neighborhood without getting out of that, right? And one of the ways to ensure that you can really improve your meta-heuristic is to consider this diversity of the solution. So when you make a swap, or you make a change or a local move or whatsoever, try to evaluate if that really brings some diversity into your solution. Just don't do it, blindly somehow, right? Second point is, then once you implement your heuristic of choice for your problem of choice, then you have to decide about the data sources. If you use random sets, you'll be happy. Most likely your paper could be published, but for real purposes, then perhaps you have not got the best picture of the system, right? So using data sources from real data sources, like traces from workload archives, public repositories, etc., could give you much better insights on the challenges of optimizing the problem, right? And likewise, simulation environment is very important. Obviously, some people, that would be perhaps the easiest way is they try to implement an ad hoc simulator. What I don't want to save is energy. Okay, I'm going to make a simulator that focuses only on energy. Perhaps a wrong choice, because you miss many more details of the infrastructure, right? So it would be very good also to get a simulation environment that is representative for the community, because in that case, you can have more feedback and others can reproduce your experiments, right? And finally, remember that any meta-heuristic that uses random decision inside needs somehow to have, we need to have some evidence that what we get at the end is statistically significant. Means that if someone else runs your implementation under the same setting, under the same parameters, it is expected that it will get the same optimization values. If that's disparate, means that perhaps your results are biased, and obviously we should try to avoid the biased results. All right, so I think I'm done. There is also a huge demand on publishing on this big data and optimization, etc. So I've started the edition of 2 book series, one with Springer, another with Elsevier. You can look at some of the volumes are also, I think they are free to access. Or if you'd be interested on some particular chapter, you could contact me. So, and obviously there are many people, more than 25. We have recently started this about 2 years now. But there are more than 25 volumes published. So there is a huge demand on publishing these things. So that's it. Thank you very much for coming and for listening.
Fatos, it's always very interesting to hear you and explain these wonderful ideas. So, time for questions? Good.
Well, good morning, and thank you for a very nice talk. Yeah, we've seen what it's been done in the academic world regarding this problem of optimization. What is being done today by the companies? Which strategies are they using to tackle this problem?
Yes. So the question actually is somehow a question that Elena did in a previous meeting that we had a few days ago. So who are the players in the big data domain or in the cloud computing nowadays, right? And as a matter of fact, those who are really doing the big data and the cloud computing are the big players like Google and Amazon and others, right? So small and medium-sized companies are not doing any kind of optimization. So they just use their cloud computing, either private or like off-the-shelf solutions, right? Big companies usually have two strategies, like Google, for example. First is use brute force. If you need more resources, you put more resources. They can afford that. The other one is optimization. So I know, for example, that Google, when they started to look at the energy, so I mean, they don't look at the problem until they have the issue in place, right? And when the Google started, having thousands and thousands of farms of computers, they obviously run into the energy problem. And they started to optimize, and they optimized up to 70–80% of the energy. So that was really amazing. Means that if you make brute force solution, you really are spending a lot of energy. And they just by doing some not very sophisticated optimization, they just by allocating things into the correct machine, switch machines off and on according to the number of applications, migration, etc. Right? So even by simple meta-heuristics, you can get a good optimization. You need not to make sophisticated optimization, right? I think for big companies, because the priority actually is the service level agreement, well, the benefit of the service level agreement, they are interested in the optimization, but they are very much interested in the elastic scaling up and down. So, and obviously, if you'd like to optimize, that would give some overhead and also some time to make the computation. So in most cases, big companies go for brute force solutions, and obviously when the problem they do optimization, but I've not seen anything like big concern at big companies to make the optimization as a first solution for their platforms. Maybe in the future, when they will run, by scaling and scaling and scaling, you come to a point that managing the whole infrastructure becomes really very complicated, right? So maybe at that point they will think again and have put more optimization techniques into place. So the whole thing is, though the difficult thing is, okay, I have a nice implementation about energy consumption. Now I need to integrate it in the data center pipeline. And the integration into data center pipeline, which makes the problem more difficult, because you may keep changing the configuration in data centers. Your policies about serving to users may change, et cetera, right? I don't know if yeah.
Thank you so much. One more question.
You said that in CloudSim you use a snapshot of your distributed system. So my question is, how do you go from simulation of the scheduling of tasks or whatever to the real implementation in real time?
So I mean, the snapshot for the static case.
Okay.
Only for the static case.
So
I look at the system. So first I get the planet Java. I can get the real numbers. Yeah, so in the static case, I first get the traces from the Planet Lab, so to get the numbers, for example, for the machines, like a million of instructions per second, etc. So when you go to the simulator, instead of putting numbers, at random, you put sort of real numbers, okay? Then you make the snapshot, means that you look at the system at that moment, and you get the instance of the problem. And once you have the instance of the problem, you run your meta-heuristic optimization, and you get the assignment. Then you go back again to the simulator, and then you make the real assignment. All right? And then at the end, you look what was the energy, compare the energy that, according to different policies. For example, one policy would be use the policy of SimCloud, or CloudSim, sorry, by default. Because CloudSim has by default energy simulation policy, right? So it has its own policies. Then if you make default policies of the CloudSim, you compare them with your meta-heuristic, and you see if you really have a good gain or not. But that's for the static case. For the dynamic case, likewise, you get the numbers from the Planet Lab files, because you want to make profiling more realistic, right? When you generate machines and you generate the types of virtual machines, etc. But then what you do is a loop all the time. So you are not finishing. So you are looking at a time window and say within, let's say, a day, we had long simulations in CloudSim, like 1 day, 2 days, 3 days, right? And you have to see if you really, within a time frame, you have an optimization in terms of the energy. Obviously, you cannot look at 1 hour or minutes or hours or even a few hours. So you need to look at, at kind of longer window times. Yeah.
So the idea would be to create policies to update your policies to optimize after a few times. So in the static case, it's to update your policies to optimize your current distribution.
In the static